right, so let's continue with our lecture about dimension reduction. So last Wednesday, we had a holiday this Monday. So our last lecture was last week. So we talked about the PCA in detail. So the PCA is a linear dimension reduction algorithm, the most popular algorithm. And actually, I have to say that this algorithm, the way we introduce it, is not involving much statistics, right? We are not talking about random variables, or actually a little bit, but here it's just at the observation level. So when we say we want to maximize the variance, we are looking at the end observations. So we just talk about observations. We didn't talk about the population underlying the random variable. So the whole discussion we give you is from the sample perspective, only the end observations. So it's an algorithm. And the key of the PCA is to find a combination of the original P features, okay, a linear combination of the original P features into a new feature. And we call the coefficients as the loadings. So the goal is that for the first new feature, we want to maximize the variance of our n observations in this new feature. Okay, using that, we solved this optimization problem and we led to this interesting eigenvalue solution. So in other words, the eigenvector corresponds to the largest eigenvalue of this X transpose X matrix, a P by P matrix. So you can consider this to be like the unstandardized sample covariance matrix of the original P features. So we standardize each feature, or I should say we center each feature so each feature has zero mean. And whether we do the standardization or not depends on whether we believe the original P features are in the same unit or not. If they're already in the same unit, we don't want to standardize them. Otherwise, we will standardize them. So that's case by case. But we will center them most cases. And then this is the centered X transpose times the center X, that gave us a P by P matrix. And this matrix first eigenvalue, the largest eigenvalues corresponding eigenvector will be the loading vector to get our new dimension, first new feature. Okay, so then if we multiply our matrix with this loading vector, so basically X times this phi 1. Phi 1 is p-dimensional vector. So X times phi 1 give me a n by 1 vector, right? It give me an n-dimensional vector. And that vector is what we call the PC1. So the difference between the loading vector and the PC1 is you involve the original X matrix or not. So the loading vector is p-dimensional, while the PC vector is n-dimensional. So PC contains the coordinates of your n observations in the new dimension, while the loading vector is the coefficient of the original P features that will give you the new feature. Okay, so that's PCA. So just remember that when we do PCA, we start from this X matrix, n by P, n observations, P features. Okay, so next we introduce the multidimensional scaling called MDS. So multidimensional scaling has a different input as PCA, from PCA. So the difference is that here the input is an n by m distance or dissimilarity matrix. So you may not have access to the original n by p matrix. You don't have the original p features. You just have some sort of process data, like the end observation, how different they are from each other. And what kind of data is like that? So I can give you one example, like a network data. So if you just know the connectivity of your n observations without knowing the underlying features that drive the connectivity, in that case, your connectivity matrix can be regarded as a similarity matrix. And if we do 1 minus that, that will give us a dissimilarity matrix, and that could be our D. Okay, so starting from this D matrix, our goal is to find a low dimension embedding of each observation. So we call them Z1 to Zm. And in the MDS, usually the R is just equal to 2. So usually we just want to find a two-dimensional embedding. So therefore, in the two-dimensional space, say R equals 2, then let me just say often r equals 2. So in this case, we want to have the Euclidean distance between two observations in the embedding space being as close as possible to the Dij in the input. So that's the purpose of MDS. So in other words, we want to find some points in a low dimensional space to reflect the input distances. So we will talk about the classical MDS in this class. So our goal is to find this. So let's say this Z1 to Zn is our target, right, to find. So we want to define a gram matrix. So the approach, okay, is to define, this is called a gram matrix. Probably the G should be capitalized. So the gram matrix is actually based on the target Z1 to Zn. So let's see that we find this, maybe I'll write this first. So I'll define the gram matrix B as Z times Z transpose. Okay, so where the Z is just a stacked matrix of the low dimensional vectors to be found. So I call this Z1 transpose to Zn transpose. In other words, I put each Zi as a row. So this is an N by R matrix. Okay, so you see in this definition, this is B is N by M. This is a gram matrix. And also, you know, to find those embeddings, I don't care where their centers are, right? Because I just care about their pairwise distances. I can shift them all together. So therefore, it makes sense to assume that we have in each of the R dimensions, the sum of Z1 to Zn is 0. So we're going to assume that. So basically, assume that. So let's say that for each J, should I call J? Sure, okay. So maybe for each J from 1 to R, I from 1 to N, I from 1 to N, okay, Zij is equal to 0 for any J from 1 to R. Okay, so in other words, we assume each dimension in the embedding space is centered. Okay, so then given this, and our goal is that we want to find the relationship. So suppose that we want, and that's actually what we want. Suppose we just want this Zi minus Zj equal to Dij. Okay, then we want to find B. So from here, the question is, how can we find B? Okay, if we can find B matrix, then we are basically done. So given this B matrix, we can just do Eigen decomposition to find Z. So if we can find this B, we just do Eigen decomposition to find Z. And we are done. So this is the whole idea. So in other words, we want to go from this D matrix to the B matrix, and then to do Eigen decomposition to find Z. Okay, so how do we do it? So in order to do that, we need to find the relationship between the entries in D and the entries in B. Okay, so basically, let's consider the Dij. Let me see the page. So the Dij is our input. Okay, we start from here. And we want to set it to be equal to the Euclidean distance between my to be found Zij. Okay, and let me square it so I can open it up. And we know what? We know this Euclidean distance square can be defined as just Zi minus Zj transpose times Zi minus Zj, right? This is how we can write the squared Euclidean distance. And then we open it up. So we are going to find this is equal to Zi transpose Zi plus Zj transpose Zj minus 2 times Zi transpose Zj. This is what we will have. And then you can see if I define the entries in my grand matrix B, okay, in this B matrix, if I write it as Bij, so it's ith row, jth column is called Bij. If that's the case, then we can express that relationship, the one I just wrote about, is equal to, and also B is equal to Z times Z transpose, okay? So in other words, if I look at this Z matrix, this is the Z matrix, right? And its transpose can be written as, let me just go to one more step. So you can see the Bij, okay, is the ith row, jth column in B. Then what is that? It's basically equal to Zi transpose times Zj. This is the definition of Bij. Okay, then coming back here, then you can see this is exactly Bii plus Bjj minus 2 times Bij. Okay, so you see, this gives me a relationship between the D matrix and the B matrix. So in other words, I could directly solve I could find the Bij for any Ij based on the Ds. So I will skip the details. I guess I should skip the details. It's basically algebra, right? Given the Dij square equals this, using this relationship, you could play with algebra and you could just solve what is Bij finally. So we can show that Bij is equal to -1/2 of Dij square minus D dot J square minus Di dot square minus Dii square. I think the last one might be plus, actually. Yeah. So minus, yeah, I think the last one should be plus. I think it was a typo in the notes. So here, what are the definitions for these things? So where the D dot J square is just equal to the average of Dij square, I let I go from 1 to m, and I keep J. So it's basically the squared D matrix, and I took the column J's average. That's it. And then the Di dot square is the average. I let J go from 1 to n, and I fix I. So it's the row sum of D square. And finally, the D dot square is 1 over n square. I and J both go from 1 to m. The overall average of the D square matrix. Okay, so doing that, I could obtain the Bij. And then with the B, we just do Eigen decomposition. So since B matrix is square, right? And also it's positive definite. So with this, we do Eigen decomposition on B. We call the decomposition as V times sigma times V transpose. So it's the same V, then it's transpose on the right. So let's see that if if the lambda is known to be a diagonal matrix, right? So let's see what the dimension of B is. We know that B is m by m. So we could actually write this eigenvalue decomposition, this diagonal matrix, we could just write it as lambda 1 to lambda m. So because the diagonal has n elements. But what we could do is that given what we want, right, the thresholding, and it could be that some of the eigenvalues are 0. That's possible. So the lambda 1 to lambda m are ranked in a decreasing order. And then given the r we want, we just truncate the top r here. So let's say this is r dimensional here. So in this case, you are just going to have this v to keep its first r columns. So if I just write out this v, so if we write as v1 to vm, we only keep the first r columns that correspond to those r eigenvalues. And similarly for V transpose. So if I define this to be VR, right? So this is an M by R matrix. And now this lambda R is an R by R diagonal matrix. So if I do that, then finally I would define my Z as just VR times lambda R to the 1/2. So in other words, this means that in this lambda R 1/2, what I'm having is just the square root of lambda 1 to the square root of lambda R. That's it. That's this diagonal matrix. Okay, and then this is my Z. So you can see this Z by definition would be N by R, and each row is the embedding I find for each observation. So here the basic idea of this MDS is still in Eigen Decomposition. And you can see the connection between this and PCA. If I can tell you that if the matrix or input matrix, if the input D matrix, okay, is Dij, has Dij equals to the Euclidean distance of xi minus xj from our X matrix, where xi is the ith row of that matrix n by p we deal with in PCA. If this is the case, then the MDS we just introduced is exactly equal to PCA. So they do the same thing. But you can see MDS is more general. It is not restricted to saying you have this input matrix and doing the distance calculation based on Euclidean distance. You could define the distance in any way you want, and then you can just follow this procedure to find embeddings that preserves the Euclidean distance. Oh, sorry, that preserves the input distance. That's it. Okay, so I think it's a very cool idea. And it hasn't been, I think it hasn't received enough attention nowadays, but it's a very classical technique. How you derive that formula for Bij in terms of Dij? Okay, so if you want to understand that, you can check the lecture 9.pdf on the CCLE homepage. So it was the typestat note from the previous chat, but I can briefly show it to you so that you know how it's derived. So basically, we need those relationships. So given that from here, we have this Dij squared equals to Bii plus Bjj minus 2 Bij, right? So everybody is okay with this relation. Then starting from here, then if we take the sum of Bij, let I go from 1 to m, then this is the definition. Okay, so in the notes that we use y, but in my writing I use z. So you can just pretend that z is yz. So it's this one, and then we just expand it and we show, because we centered each yik, right? So my zik. So then this is 0. So we will have this Bij sum for I 0. So therefore, if you take the sum of Dij squared like this, it will be equal to the trace. Trace is the sum of the diagonal elements of the matrix B. And this is the sum for I fixing J. If you do the sum for J fixing I, you're going to get the same thing.
But you have the n times bjj here, n times bii here. And finally, you are going to have this double sum equal to 2n times the trace. So you can see that you can solve for the trace by dividing 2n to the left-hand side. And then you can put this trace back to this formula, and then you can solve for the BII, right? So once you solve for the BII, and then finally, you can go back to this formula. So you know BII, you know BJJ based on the D, and then you can solve for BIJ. So that's how it works. Okay. So then let's go back to the next method. Okay, that's MDS, which is a classical method for doing embedding. And it's also linear embedding, right? You didn't do any nonlinear operations. So the next method I'm going to introduce is what's very popular nowadays in the single cell field, the t-SNE method. So before I talk about t-SNE, I will talk about what the first version is called a SNE. Okay, what it stands for is stochastic neighbor embedding. Embedding. So what's the difference between, and it was proposed by the famous Hinton, who got famous because of his contribution to neural network, and I believe it must be his student. So this SNE paper was published in 2002, and the t-SNE, which is a modified version of it, was published in 2008. But interestingly, the t-SNE paper wasn't become like a, I would say, explosion until the single cell technology arose. People found that it worked very well for embedding the cells. So you can easily see the cell groups, clusters. So that's why it became interesting. It became popular. So this story tells us that every computational tool needs a proper application domain so it can be useful. Okay, so here the goal is that the perspective is different from the MDS. In the MDS, you want to preserve the input distance. And here you want to preserve like a local pairwise density. That's what it tries to do. So here the input data are the original feature vectors. So not just the distance matrix, but just like PCA, we need the actual data. And every observation is p-dimensional. Okay, P is a large dimension, large number. And then our goal is still to trying to find the output. Also, I'll stick with my notation, Z1 to Zn. Okay, so still a much lower dimension. So P is much greater than R. Okay, so what it tries to do is that it tried to convert the pairwise distances between 2 points in the high dimensional space. So let me call this high dimensional space. Again, this is the low dimensional space. So what it tries to do, it will try to convert the pairwise distances between 2 observations in the high dimensional space into a density. Okay, so this is defined as P, J, given I. So you are treating Xi as the center of a normal distribution. And then you are going to compute the density of Xj given that normal distribution. So we know that the normal distribution, if you assume to be a normal distribution, we can say it's proportional. Let me start from the idea first. It's proportional to the exponential function of the density of the distance, xi minus xj. Okay, I calculate this distance, squared it, divide by 2, and I need a variance for this distribution, sigma I squared. So basically for each xi as the center, it has its own variance for the distance density. Okay, And they want to make, so this is for j not equal to I. Okay, so what they want is to make the, for all the j doesn't equal to I, this probability to be normalized. So the normalization they want is that for any j doesn't equal to I, pj given I is equal to 1. Okay, and they also want to have this point I. Okay, so this probability, I may give you the idea first, is the probability that I picks j as its neighbor. So this is the intuition. And you can see that the smaller the distance, the more likely I is going to pick j as its neighbor. But they don't want I to pick itself, because you can see when this numerator is 0, right? We know the exponential 0 is 1. So actually this is not equal to 0, but they want it to be 0. So they want to force pii equals 0. So in this case, I will not pick itself as its neighbor. So with all the thoughts into consideration, the normalized version is for pj given I is equal to what we have here, exponential negative xi minus xj square sigma I square divided by the sum of all the k doesn't equal to I, the same thing applied to xk, xi minus xk square 2 sigma I square. Okay, so this is the case for j doesn't equal to I. If j equals I, this is just equal to 0. Okay, so they define those probabilities based on the densities in the high dimensional space. And the density is defined by the high dimensional pairwise distances. So in other words, they are not preserving the high dimensional distances per se. They are converting the distances first to the sort of density, normalize into probabilities, and then preserve those probabilities. Okay, so in the low dimensional space, so these all happens in the high dimensional space, okay? In the low dimensional space, to find the zi, zj, they want to mimic this idea. So basically, they want to define qj given I as the probability that I picks j as its neighbor in the low dimensional space. And here, because the low dimensional embedding is our choice, right? We should choose how they are spread out, whether they're very densely clustered together or they're more evenly spread out. So in the low dimensional space, they actually assume this variance for the density for point I in the center. They assume this variance to be fixed at 1/2. Okay, so in this case, you see, fixing this at 1/2, we would have this as what? This would be just, I'll just write here. So it would be exponential, the same. And it will be the Euclidean distance between, sorry, I should say zi and zj squared, the low dimensional space, because we set the variance to be 1/2 for all the I in the center. So 2 times 1/2 is 1, it's gone. Normalized by all the points that doesn't equal to I. Zi minus zk. Okay, so for any j doesn't equal to I, this is the low dimensional probability that I picks j as the neighbor. And it's 0 if j equals I. Okay, so this is in the low dimensional space. So now you can imagine how many such probabilities we would have. For every point I, we would give it n probabilities because this j can be from 1 to n. And then for another I, it's going to have n probabilities associated with it. So it's n squared, right? So for every point, it has n probabilities, which means the probabilities of picking one of the n points as its neighbor. Okay, so we would actually define this as a vector. So we define the vector P, capital Pi is basically as the vector of the probability 1 given I to n given I, right? We let j vary from 1 to n. It's a column vector, so I put the transpose here. And the qi is for the low dimensional space, q1 given I to qn given I, transpose. Okay, that's it. So Pi is n-dimensional, Qi is n-dimensional. And the goal is to make Qi as close as possible to Pi. So that's the goal. Make Qi close to Pi. How do we address this issue? How do we make two probability vectors, right? So each vector sum up to 1. That's by our definition. How do we make two probability vectors close to each other? And we can use the so-called Kullback-Leibler divergence, KL divergence. So the objective function or the loss function we want to minimize is the KL divergence. And this is actually from from information theory. So let's say that for the KL divergence between Pi and Qi. So we are using the Pi as our basis. Okay, and the Qi is the thing we want to find. So Qi is the target, Pi is what we have, the reference. So usually we use the double vertical bar to separate Pi and Qi. So this is defined for all the elements, the probabilities. Here we have n elements. So we let the j go from 1 to n. And it's defined as Pj given I times the log of Pj given I divided by Qj given I. Okay, and we can see that we can see easily that this KL divergence is 0 if all the Qj given I equals Pj given I. So this is log 1, and that will give me 0. So this is a KL divergence for the ith point in the center. And of course, we want to look for all the points. So therefore, it makes sense to just take the sum of the KL divergence for point I. So let's take the sum for I, go from 1 to n, and I from 1 to n. That's the objective function or loss function to be minimized. So therefore, it becomes just an optimization problem. How to find this Qj I given I for any I and any j, then we can minimize this. But that's not done yet because Qj given I is just an intermediate, right? We ultimately want to find the z1 to zn. So in other words, let's see if we call this cost C. What we really want to do is to find the z1 to zn that minimizes the C. This is the goal. So then the algorithm they used, a common algorithm used to solving this problem is called the gradient descent algorithm. So by gradient, we mean that we take the partial derivative of C against each of z1 to zn, and that gives it the gradient. And we want to follow the gradient and go down in that direction because that will drive the C function value to a smaller value. So that's that's what the algorithm actually that's used in the deep learning neural network. We use gradient descent. So here the gradient descent algorithm. Okay, let's just show you one case. We do partial c function, partial zi. Okay, and of course we know zi itself is also a vector. It's r-dimensional. So we just treat it as a vector differentiation. And then we are going to go to this complicated form, for this qj given I, it depends on z1 to zn. So basically, when we do the differentiation, we are going to use the chain rule here, right? So we can go to the z1 to zn. So by the end result in the paper, it's just having this nice form is equal to 2 times j go from 1 to n, and that's from here, j go from 1 to n, times pj given I minus qj, so qj given I still stays here, plus pi given j minus qi given j. You can see the reason as that zi will participate in both qj given I and qi given j, right? Because it can be the center or it can be the neighbor. M times, I think this should be, yeah, the gradient, exactly. So the gradient exactly is a vector. So zi minus zj. So for all the j from 1 to n, this is the gradient. Okay, so actually they give, I think the machine learning people are very good at giving names to the terms, the mathematical terms, to make sense of them. So they call this term, I think it's a very interesting name. They call it stiffness. Okay, and they call this the length. Okay, so what it means, what I think my interpretation is that here, the stiffness is actually about how similar, right? So the two probabilities, one in high dimensional space, one in low dimensional space, how similar are they to each other? So it's like so the larger the gradient, the more you will go in this direction. So this length is about the difference between these two values, I would say two vectors in the low dimensional space, zi, zj. And given their difference, and also this stiffness, the similarity between the current q and the p will decide the step, right? How much you go. So if they're already very small, then you don't have to go much. So therefore, you can see this trade-off the current similarity, how much it will affect your next step. Okay, so given the gradient, okay, so the gradient descent algorithm will update your value based on the current value and the gradient. So you will go a step in the gradient direction. And sometimes people may want to also have some force to drive it back a little so you don't go too much. So in other words, in the iteration, tth iteration, you are just going to update your z, I, t, the tth iteration value based on its previous iteration value, the current value, and you are going to go by a step size. This eta needs to be a fixed parameter. You set it in the gradient direction. Okay, in the gradient direction, given the current value. And then you add some force to drive it back. So usually this is another parameter people will set, and it depends on how different the value is between the current t-1 value and the previous t-2 value. So in other words, you are trying to not just move forward, but you also have some backward thing, okay, going back a little bit so that you don't move too fast. So this is just a typical way of doing this optimization in the gradient descent algorithm. Okay, so that's it. So basically, you are going to just do this until your algorithm converges and it doesn't move, and the Z1 to Zn are not moving anymore, are not changing anymore. And one more thing to say about this algorithm is that it has this thing called perplexity. The perplexity is used as a way to set, you know, these ones, don't forget, sigma 1 squared to sigma n squared for each xi as the center. These needs to be pre-specified, right? So to address this question, how to set sigma 1 squared to sigma n squared, which are needed for that pj given I calculation. For this question, the authors proposed a criterion called perplexity. Okay, the perplexity is defined also in terms of the entropy. So it's defined as two, or I should say, maybe just, yeah, give the notation. Perp is defined for each pi, and pi is this vector with I in the center and picking other points as the neighbors. Okay, this probability vector pi's perplexity is defined as 2 to the power of the entropy of pi. And this is the Shannon's entropy. And it's defined as 2 or negative summation j from 1 to m pj given I times log of p, this is log 2 of pj given I. Okay, so that's the entropy. So in other words, you can see the sigma I is involved in pj given I, right? So this pi depends on sigma I. This is in the formula. Sigma I is involved. So therefore, to set the perplexity to a constant, if you set, say, perp pi equals to 10, if that's the threshold or the value you want for the perplexity, you can solve for the sigma I. And you could do that for all the i's, I from 1 to n. You could do that. So in other words, you still allow each point being the center to have the different sigma I, or maybe I put sigma I squared, to have a different sigma I squared. But you set the perplexity to be the same. So you can imagine what would happen when the sigma I increases. Okay, look at here. So when sigma I is large, it's just like in Gaussian distribution, the variance is large. So the density will be broader, right? And being broader means what? More neighbors will receive a similar probabilities. So in other words, the probability pj given I will be more even for different j's. So it's more spread out. And being more even, going to the entropy of this probability vector, the entropy will be bigger because entropy measures the uncertainty. So if in this vector, these values are equal to each other, that maximizes the entropy. If only one of them is equal to 1, the others are 0, that's the certain case, then the entropy is 0. So basically you can see as sigma I increases, entropy increases, perplexity increases. So setting the perplexity, you have a monotone relationship with the sigma I. So making the perplexity larger, then you are going to consider more points as neighbors. Or in other words, the t-SNE algorithm is less local for preserving the densities or preserving the distances. But if you set sigma I squared to be slow or perplexity to be low, then you are going to preserve more of the local structure. So let me just write this. So it depends on this. The larger sigma I squared, the larger perp pi. Okay, So that's the SNE algorithm, the 2002 algorithm. And I would say probably the default perplexity is like usually 10, 20, 30 or something. So, but you can see this is a tuning parameter in this algorithm, and it will affect the result. And also the gradient descent algorithm is not deterministic. So it will be based on where your initialization is. So that's why when you run it with different random seeds, you may get different embeddings. Okay, so that's the 2002 paper, but in the 2008 paper, they tried to improve SNE or modify SNE in two ways. So the t-SNE, which is the algorithm now we use in the single cell field. So this is from another student of Hinton, Van der Matten, and Hinton in 2008, okay, after 6 years. So they made two modifications. The first modification, the first one is that they want to make the, I would say, the cost function here symmetric between I and j. Okay, so currently, or in the SNE paper, it's not symmetric. So j given I is different from I given j. And making them symmetric is a good, so making them symmetric is a good way to make the gradient simpler. I think that's the main reason. So they want to simplify this cost function and therefore its gradient. So I will call this symmetrization. So in this case, what they did is that they would like to define Pij in the high dimensional space by averaging Pi given j and Pj given I. Okay, so by averaging, we're going to divide them by 2. But not there yet. Since you are going to now assume that, so basically you are now going to assume this sum of Pij, double sum, I from 1 to n, j from 1 to n. So now you want this to be summed up to 1. But if you remember in the previous one, it's just Pi given j sum up to 1, right? So, but you know, for the Pj given I, let me just put this way. So j from 1 to n, this sum to 1. And if you add a sum, I from 1 to n, j from 1 to n, then Pj given I will give me n instead of 1. So therefore, you want to divide n here to satisfy your current need. You want to make the Pij all sum up to 1. Okay, so this is the first change they used to try to simplify the gradient. And the second change is trying to change the low dimensional distribution from a normal distribution with variance 1/2 to a student t distribution. Okay, so the low dimensional distribution with variance 1/2 is going to change to a t student t distribution. This is the formal name. This is because of the student t test, which introduced the test, and the test statistic distribution under the null hypothesis is known as the t distribution, which we introduced in the beginning. Okay, so why would they pick the t distribution? Actually, the reason is that they want to use this important fact about heavy tail, that t distribution is more heavy tail than the normal distribution. So let me just give you this interesting density comparison. So let's say this is 0, okay? And let's say that our normal distribution looks like this. Okay, this is, I'm just going to use the normal, standard normal for example. Okay, and then what a t distribution look like, it would be more heavy tail. So I'm going to draw a more extreme version. Okay, So in other words, those larger values far away from 0 will have larger density. So this is the t distribution. And because each density must have area equal to 1, right? So that's why if they are higher here, they must be lower here. And then what you can see is that the density is a way to reflect the distance. Okay, so basically for the same distance, let me put it here. So if the distance is close to 0, and actually we only care about the positive domain because all the distances are non-negative. Okay, so if this is the zi minus zj small, okay, so when 2 points are small, then you can see that the density they receive from t is lower than the density they receive from normal. Okay, so changing, let me mark here, changing from normal to t. Then for small distances, the density and as well as the Qij, low dimensional probability, would decrease. Okay, they will be smaller. But now if you imagine, if the zi and zj lies in the tail, that means when the distance is large, and the density would increase if you go from normal to t. So in this case, the density and Qij would increase. So it means what? It means that if you want to have the embeddings, right, in the low dimensional space, this t distribution would allow you to have a bigger cloud. So I mean that, sorry, I should say that this is the relationship, right? But don't forget that the Qij are going to come from Pij. So you will compute the Pij first. So the data, let me give you the logic. Data gives you Pij. And you want to match Pij to Qij as much as possible by your optimization. So Qij should mimic Qij, mimic Pij. So in other words, if 2 points are close in the high dimensional space, then Pij is small. So let me just put it here. So 2 points Ij close. Okay. If that's the case, then Pij is large. And Qij is also going to be large. Okay, and then from the Qij, you are going to find Zi and Zj. Okay, Zi minus Zj is going to be coming from Qij. So their distance in the low dimensional space. Then let's see. That's the density. Qij depends on the density. So if the density is large, okay, somewhere here, that's the density y value. Then the same y value will give you a smaller distance under t than under normal. So then you can see this z and zj will be smaller under t than normal. Okay, now if the other case, if ij are far away, then the Pij is small, Qij is small. Then when we look at the low density right here, very close to 0, find the corresponding distance. Then you will actually go far away in t than in normal. So in other words, Zn minus Zj will be larger under t. So you see the effect. So going from normal to t, you are going to pull close points closer in the low dimensional space. And you're going to push far away points farther under t in the low dimensional space. So that's why using t than normal instead of normal will give you a more extreme presentation in the low dimensional space. So that's the reason they change from normal to t using the heavy tail property. Okay, so that's for the second change. And the first change is more from the optimization convenience perspective. And that's t-SNE. So hopefully I give you a general idea about what's behind the popular algorithm. And now in the single cell field, many people switch to using UMAP instead of t-SNE nowadays. However, there's a very interesting paper if you want to check it. It's called the it's called a okay, something. It's actually it's trying to clarify the mystery, right? Trying to clarify the mystery of UMAP. People say, oh, UMAP is better than t-SNE. However, the author, I think it's a Nature Biotech paper last year published, they found that it's really depending on the initialization. So if you use just a random initialization for both UMAP and t-SNE, the claim advantage of UMAP is not as obvious. But if you give UMAP a nice initialization, then it will perform well. So I think that's a very interesting finding. And also, I think the UMAP paper is actually very difficult to read if you are interested. It's still an archive paper, and it uses a lot of the topology stuff. So it's more like manifold learning, trying to preserve the manifold of x1 to xn in the high dimensional space. So manifold means that it's a low dimensional structure in the high dimensional space. So even though x1 to xn are in p dimensions, but their structure can be explained by a much lower dimension. So the UMAP math is very complicated, and we're not going to talk about it here. But yeah, so the basic idea, I would say, still trying to preserve some local structure from high dimensional space to the low dimensional space. So their perspectives are very different from PCA and MDS, because PCA just preserves the global variance. So it's a global perspective. While in the t-SNE stuff, you see these kind of density, because we know the Gaussian density is very light tail, right? We know that the 95% is within like 2 sigma from the mean, right? We know that result. So therefore, you can see that when xj are far away from xi, we can easily shrink its probability of being picked as 0. So therefore, that forces you to focus on the local neighborhood of point I. Okay, so that's t-SNE. All right, any questions before we continue? So far we talked about PCA, MDS, and t-SNE.
Hi, yeah, I had a couple of questions. The first one regarding multidimensional scaling. I just wanted to clarify one aspect. So basically, when we obtain the B matrix, in principle, this is n-dimensional, right? And then after eigenvector decomposition, we write it as B lambda B transposed. And then, but here on the V vectors, it's not like it's not a given that from R+1 to n all the components are 0, right? So this is something we enforce on V.
I'm sorry, I missed that sentence you said.
Yeah, here you write that we select only the first R values of V.
The first R values, yeah.
And this is enforced, like it's not in principle after eigenvector decomposition, V has got all the components, right?
V is what components? Sorry, so basically the order of the V's follows the order of the eigenvalues. So the eigenvalues are sorted from the largest to the smallest. And some of the eigenvalues may be zeros.
Yeah, and after taking only the first components of V, the relationship with the original distance matrix is not anymore a perfect equality, right?
Right, it's not perfect. So that's why we start from the perfect case and then we do the truncation. Similar as PCA, if you go to all the PCs, right? If you have original P dimensions and if you keep P PCs, you don't lose any variance. You preserve the original variance 100%. But when we do PCA, we truncate that K PCs. So that K is our new dimension number, which is the R here. Yeah, exactly. So when you have this truncation, then Z times Z transpose is no longer equal to B, for sure.
Yeah. Okay. And then, for t-SNE, I was just wondering, like, what is the advantage with respect to the other methods? For instance, like if we use MDS using a dissimilarity matrix very similar to to the exponential average we had in P. Sorry.
Yeah.
SNE.
So this Gaussian density is the key. So this one in the high dimensional space, you can regard this as a nonlinear transformation of the high dimensional Euclidean distance to a value. As I said, the Gaussian has that light tail property. So basically, you are not giving this when x and xj are large, or this distance is large, then you can easily shrink it to zero, close to zero. So that's why when you preserve the pj given I, pi given j, you are only focusing on those close pairs, the neighbors, and the faraway things do not affect your embedding. Yeah, so that's why in the t-SNE projection, you can easily see those very well-defined cell clusters. Yeah.
Yeah. And would we get something similar if we use multidimensional scaling using a distance?
Yeah, exactly. Actually, a student of mine tried this, but we didn't actually pursue that as a research project. Exactly. So if you use the symmetrization version, right? Let's say you do the P, you get a P matrix, and the matrix is symmetric now. And now that can be regarded as a similarity matrix. And what if you do 1 minus P? That gives you a dissimilarity matrix, and you can use MDS to find the embedding. Yeah.
Yeah. Okay.
Yeah. So I would say that is not exactly the same as the t-SNE for sure, because t-SNE has that, complicated thing, and you also have that Qij to go back there. But that you have the T distribution in low dimension space. But I would say if you try that, yeah, you can try that, and you can see that just using the P to do MDS, you can see better separation than using the Euclidean distance in the high dimension.
Okay, I see.
Yeah.
Thank you.
Okay. That's a great question. So, okay, all right. So the last thing I want to, not last, but the second last thing I want to say is also something good to know, but not so popular in bioinformatics. I guess maybe used more in like signal processing, those kind of applications. And this is called the Independent Component Analysis, ICA. Many people confuse it with PCA because of the similar name. And also many people are confused between what we mean by uncorrelated and independent. Actually, from a probability perspective, these two are only equal to each other when the distribution is Gaussian. Right? In the Gaussian, two variables, if they're bivariate normal, then they're uncorrelated, implies they're independent. But in other cases, more general cases, it's not the case. You can have uncorrelated variables that their correlation or covariance is 0, but they are independent, they are dependent. Okay, so the independent component analysis is trying to, you can consider this to be decomposition. Okay, so basically the key idea is that we have some signals that are measured, but you believe that they come from independent sources. So let me just give you the example, which is stated in very detailed way in our notes. So this is from like if you are measuring sound in the room, okay? And you believe that the room has 2 microphones, and these microphones have a person standing in front of it and speaking into it simultaneously. So those 2 sources are independent. So person 1 speaks what has nothing to do with what person 2 speaks. So they speak independently into 2 microphones. And then what you do is that you measure the total sound in the room in 2 places. So one place you just collect the sound from one location, and then another location you collect the sound. So you're going to use your collected sound and try to decompose them into the 2 persons' voices. So that's the motivation of this problem. So that's why we call it signal processing, right? Try to identify the original sound based on the measured sound. Okay, and the soundtrack changes with time. So it's a time series, it changes with time. So let's call that here This is our measurement at location 1. We denote that as x1, and it changes with t. Okay, t is the time. And at location 2, we measure x2t. Okay, and we believe that each is a combination of the person 1's voice at time t. So we call that S1t and S2t, right? So each location's sound is a mix of those two person sounds. So I would say source 1, I denote that by S1t, and source 2 is S2t. Okay, and the coefficients, we denote them by A11 plus the coefficient is A12. So the first subscript is for the location, second subscript for the source. And here A21, A22. Okay, so here the challenge is that we don't know the coefficients. Otherwise, if you know the coefficients, you can just solve for the linear equation system, problem solve, right? You don't know the coefficients and you don't know S1 and S2t. So that's your target. You want to infer S1t, S2t. So what you have only is X1t and X2t, right? That's challenging. How do we solve this problem? So the challenge is that we don't know coefficients A11, A12, A21, and A22. We don't know any of them. And but we want to infer S1t, S2t from X1t and X2t. Right, so you can see that if there are no assumptions on the S1t and S2t at all, the problem is what we call unidentifiable. There are infinite number of possible solutions of S1t and S2t to solve it, right? So however, here the constraint is that we assume S1t and S2t are statistically independent. So to make the problem identifiable, we need assumptions on the two S1t, S2t. We assume S1t is independent of S2t. Okay, so this is why we call independence. So clearly you see S1 and S2 are variables. They are driven by the changes in t. When t changes, S1 changes, S2 changes. And when we say they are independent, we mean how S1 changes has nothing to do with how S2 changes. So basically knowing the value of S1 at t doesn't help us knowing the value of S2 at t. That's the independence. Okay, so basically in this example, we know the randomness of S1 and S2 comes from t. T drives the changes. So therefore, we can generalize this ICA into this generalization into this problem. So we have in random variables. So now we're using the probability discussion and random variables x1 to xn. And each xi is a linear combination of n independent random variables. We call them S1 to Sn, similar to our previous notations. Okay, so the number of measurable measured random variables is equal to the number of independent unknown random variables. So these S1 to Sn are latent and X1 to Xn are observable. And here, when we have that, sound example at each time t, you get a realization of each X1 to Xn. So X1 to Xn must have many measurements, multiple measurements as its realizations. So you could uncover the S1 to Sn. Okay, so in other words, writing this out, we just have Xi equals to, using our previous notations, AI1 times S1 plus AIN times SN, right? So that's it. And then if you stack your random variables into a vector, you call this X vector, which is composed of your X1 to Xn. Okay, then you can write this as the A matrix, which is equal to just this one, right? So A11 to A1m, AN1 to ANN. This is the A matrix multiplies a vector S. Okay, and S is just a vector S1 to Sn. So you can have this matrix notation to define the ICA. And the goal is to estimate this S1 to Sn, as well as the A matrix. Okay, so how do we find this, right? So here, the goal is that you need to find S, we need to estimate this unknown parameter matrix A. Because if you can estimate A and A happens to be invertible, you just multiply A inverse to the left-hand side, problem solved. That gives you S. Okay, so that gives us the estimation problem. Okay, but still, if we want to go for, so that's the basic setup. Then we have multiple ways to estimate this A. So let's say if the estimate A hat is invertible, okay, then we would just write our inferred S, this vector, by A hat inverse times X. That's the solution. So how to estimate this A is a parameter estimation problem. And multiple ways include likelihood-based estimation. So if you want to use the likelihood, write down the likelihood, do the MLE. That's one approach. But of course, we can see that you would need some distribution assumption on the S, so you can write down the likelihood. Otherwise, it's not doable. So one approach is to assume S1 to Sn, they are independent, right? They're independent and they follow some density function you specify. And there are some common choices. And from that, you write down the likelihood. Okay, based on your data, the measurements of X1 to Xn. And then you find the MLE, estimate of A hat. So that's one approach. So you can see that here, the independence will get into the likelihood, right? Because you're going to use the independence of S1 to Sn to write down a likelihood, and then you get to an optimization problem. So in this case, you can see that it's different from the PCA in that we are assuming independence. While in the PCA approach, if you think about it, even though you have the uncorrelated result based on the way you find the loadings, right? What's PC1 loadings, what's PC2 loadings, and those loading vectors as the eigenvectors of that X transpose X matrix, they are uncorrelated. However, that's not saying that we assume that they correspond to some independent random variables. That's not the case. And also in the PCA algorithm, there's actually no distribution assumption. It's just an algorithm. Although later, maybe in 2002, 2004, there was a paper talk about the probabilistic PCA, which is a probability interpretation of PCA, and it's a special case of PCA, use normal distributions. So we can see the connection between the old PCA algorithm and that probability model. However, that's not a, that probability assumption is not required for PCA. While here, when you want to talk about independence and solve it, I think this assumption about the distribution is necessary. So otherwise, how can you make sure they are really independent? So independence is something hypothetical. We don't get to observe. It's about a random variable underlying. And also, I want to say that to make this identifiable, because we know if these S1 to Sn are normal distributed, then we can rotate them in any way, and so rotating the S will give us a corresponding A, and it's still not identifiable. So this is only identifiable when these things are non-Gaussian, non-normally distributed. So they don't have that symmetry, then they cannot be rotated be rotated freely. That can give us a deterministic solution. So that makes the solution identifiable. So that's why ICA is applied to the case where you can easily assume your source random variables are not normally distributed. So for example, one typical application is like this. This is in our notes. So you can see that this is the measured signal across time. And after decomposition, you can get these two signal tracks, and they are independent of each other. So that's one application to read. So you can think about the ICA as kind of like a decomposition algorithm of signal tracks. Okay, so its application is very different from PCA. PCA is more like giving a p-dimensional data set. How can you find new dimensions that best preserve its variance? So it's very different perspectives. All right, so I think I'll stop here. And we have a question in the chat box. Since S1 are unknown, how do we compute the likelihood? No, you're going to write down the likelihood still based on the x1 to xn. But the x1 to xm is in your likelihood function, but the probability assumption is going to be written based on s1 to sn. So basically, you can write this, if you assume A is invertible, you just write S as A inverse X, right? So then when you use the joint density of S to write the likelihood, what's in the likelihood will be the parameters in A and the X. Does that make sense? Okay. Okay, so thank you for all the questions, and I will see you next Monday.
Sorry, Professor, just have a quick question regarding the homeworks. Basically, there is problem number 7, where
maybe you can share your screen if you want to.
Yeah. Okay, can you see it?
Mm-hmm.
Yeah. Okay. Yeah. In problem 7, in the last step, you ask us to do the EM algorithm to identify the parameters, and in the last question, after how many iterations are the EM estimates within 10 to the minus 4 of the maximum likelihood estimates we calculated using the complete data set. So the issue here is that me and some other students didn't get the result that the EM parameters converge to the MLE ones. Like there is never a number of iteration after which the difference between them is less than 10 to the minus 4. So I just wanted to ask you if this is normal, and if we missed something.
So how close do you see the estimates between 4 and 5?
They are about I can show you here. yeah, these are the results. So, I mean, they are pretty similar, but there is some difference. For instance, the MMILI for sigma 0 is 1.07, and for EM after 1000 steps, which is pretty much at saturation convergence, it's 0.95. So it's about a 0.01 difference.
Okay, so I think in this case it's fine. You just report what you find in the homework. Yeah.
Okay. Okay.
Yeah. Yeah.
Thank you.
Okay. Thank you.
Bye-bye.
Bye. Thank you.